Hello everyone, I'm Atusa Jawahari, a first-year PhD student from the Industrial Manufacturing and Systems Engineering Department. Today I would like to present my data mining project exploring pattern recognition in handwritten digit with MNIST dataset. In this presentation, I will provide a brief introduction and literature review on this topic. Then we become a little bit familiar with MNIST dataset, and for this project I have implemented different machine learning methods that I will discuss, and at the end we see the result of these machine learning methods and draw a conclusion. The handwritten digit recognition is a process to provide the ability to machines to recognize the human handwritten digits. This handwritten digit recognition is very useful in different fields in real world, like postal mail sorting and also bank check processing. The MNIST dataset is a standard benchmark for evaluating different machine learning algorithms in this area, and this dataset containing grayscale images of digits from 0 to 9. This project objectives are as follows. First of all, we want to evaluate the machine learning algorithms like neural network, SVM, random forest, decision tree for digit classification. We also want to explore the data pre-processing and feature extraction, and we try compare different approaches like the hyperparameter tuning to identify the optimal strategy for high accuracy. Regarding the related work, the MNIST dataset introduced in 1994, and in 1998 different researchers tried to implement its early approach to handle this dataset with different models like CNN, and after that different researchers in different universities and institutes tried to improve their model performance by reducing the error rate. In this section, we want to become familiar with the MNIST dataset a little bit more, and the MNIST dataset containing of a collection of 70,000 handwritten images, and this 70,000 is split to two sub-datasets, training and the testing dataset, 60,000 training images and 10,000 images, and each image is a 28 by 28 pixel. The dataset includes two subsets, image and the label. Image dataset consisting of the grayscale images like this, and the label dataset consisting of the corresponding labels for each image. Each pixel's intensity ranges from 0 to 255, representing a spectrum from black to white. It means that each number in the range of 0 to 255 shows a shade of gray. For data pre-processing, first of all, I loaded the dataset using TensorFlow, and then try to normalize the pixel intensity to a range of 0 to 1. And this dataset, MNIST dataset, is a huge dataset because it consists of 70,000 images, and each image is a 28 by 28 pixel. So we employ the PCA to reduce the dataset's dimensionality while returning 95% of its variance. And in this situation, we reduce the feature space from more than 700 to a smaller set of principal components, and this plot shows that a significant proportion of the dataset variance, like 90% of its variance, can be captured by a relatively small number of principal components, like 150 features. In this slide, you can see the data frequency analysis. We try to show the percentage of each digit in training subset and the test subset. And based on these two plots, each digit class has an equal number of samples and resulting in a balanced data set. As I mentioned before, I have implemented several machine learning methods that I will discuss. The first model is the decision tree. The objective of this model is to classify handwritten digits in the MNIST data set. We first reshaped the input images into a flat vector, and using the 5-fold cross-validation, we try to find the optimal hyperparameters, and in this research for this model, we tuned the criteria for splitting, maximum number of features, and maximum tree depths. We trained our models based on the 60,000 training sample from the MNIST dataset, and to test our models with 10,000 samples. The second model is a random forest. The objective of this model is like the previous model, and again we try to reshape the image into a flat vector, and using the 5-fold cross validation, we tune the number of estimators, maximum tree depths, and the maximum number of features. The next model is the k-nearest neighbors. Here again we try to flatten our image into one-dimensional array, and we try to tune the number of neighbors, weight function, and algorithms. And in all of these models, we try to find the best model based on the accuracy score. We also tried some deep learning model. The first one is the convolutional neural network, and this model is a little more complicated than the previous one, because this model has different layers with different activation function, and also we use the dropout layer to prevent overfitting, and we train this model for 5 epoch with batch size of 128, and we use Adam Optimizer. The next model is MLP, and this model also has several layers, has more complicated features, and we have input layer, hidden layer, dropout layer, and output layer. In this model also we use different activation function and different number of neurons, and we also use the dropout rate of 0.2 to prevent overfitting. This last model is a support vector machine, or SVM model. This model also wants to classify the handwritten digits, and we reshape the input images into flat vector and split the dataset into the training and validation and test dataset. We use the 3-fold cross validation to tune the kernel type between linear and RBF, gamma parameter, and regularization parameter C. And as I mentioned before, this because this MNIST dataset is a large dataset, and this SVM model is really depend on the size of data set. We used and applied the PCA to retain 95% of the variance, but reduce the number of features while maintaining high accuracy. We compare the result of these models based on 6 criteria: accuracy, balanced accuracy, precision, recalled F1 score, and training accuracy. I also show the confusion matrix for each of these models. Confusion matrix can help us to see the performance of each model better, because we can see the performance visually. Based on these criteria, the SVM model has the best performance, and the second best model is CNN, and then MLP, KNN, RF, and decision tree. The best model, as I mentioned before, is the support vector machine with 98.5% accuracy, and the optimal value for the hyperparameter tuning is as follows. The C is equal 10, gamma is equal to a scale, and RBF kernel. This model outperformed the other models in all of the criteria: accuracy, precision, recall, F1 score, and balanced accuracy. And the second best model is CNN with a 98.4% accuracy, and showing that the deep learning model can have a good performance in image classification. And the third model based on the performance is a MLP with 97.7% accuracy, highlighting the neural network versatility in pattern recognition. And also we use PCA for dimensionality reduction and reduce the runtime. In SVM model, it shows the best performance compared to other models. And this is our references, and since I have a limited time for presentation, I couldn't talk about everything in detail. You can find the detail of this project in the attached document. Thanks, Dr. Wang, for giving us this opportunity to do this project.